Happy Friday, you fabulous physics fans. Got my blue on today, repping the high, hashtag Pirate Pride 2020, hashtag once a pirate, always a pirate. Today we're going to be doing circular motion and gravitation. There's not a lot of problems to do on this topic. There is a couple of handouts at the end of my daily agenda, one on circular motion, one on gravitation, oddly enough. So let's jump into this and we'll get it done. So first thing I need to identify is what does it mean if an object is in uniform circular motion. So let me write that down. Uniform circular motion. And I'm going to abbreviate circular if that's right. Uniform circular motion means an object is moving at a constant speed in a circular path. So here's the follow-up question to that. If something's moving at a constant speed in a circular path, is it accelerating? So that's the question to think of. Yes? No? No? Yes? Is it accelerating? If you said no because it's moving at a constant speed, well, you're wrong. Because it is accelerating, because that object is constantly changing direction. Maybe it might be speeding up or slowing down, but it's constantly changing direction. So we've learned and said this over and over again, what is needed for an object to accelerate? And I hope you know the answer. The answer is an unbalanced force or a net force. So let's look at an object that is moving in a circular path. So if this is, let's say this is the center right here, and this is the object right here, we'll do it as a free body, as a square like that. So it's moving in a circular path around some center of rotation, like this, and let's say it's moving clockwise like that. So the object is moving around and around and around and around and around and around some center of rotation in a circular path. I made an example right quick, pretty lame example. I just took some string we had laying in a drawer and I tied it onto a roll of tape. I thought about a yo-yo. I thought Brett might have had a yo-yo laying around in one of his closets where toys are, but I couldn't find one, so I made something simple. So let's say you swung this around and it's moving in, let's see if I can do it. We want to go clockwise, so we're going to go in this direction right here. So it's moving around and around in a circular path. Hopefully you can see that. It's not going too far out of the frame. It's going in a circular path, and I'm trying to make it go at pretty much a constant speed the whole way. That's uniform circular motion. So at any point in the path, this object, its velocity is changing direction. For example, I'll do it in color. At this point right here, its velocity is headed off in that direction right there. For example, if that tape got right here and I were to cut that string, it would go flying off in the direction of the velocity. Remember Newton's first law, an object in motion stays in motion if the forces are balanced. So if I cut that string and remove this string, then there's nothing keeping it in that circular path. When it gets right here, when the object gets right here, you can see that its velocity now is headed in kind of that direction, off in that direction. So if I cut the string, it would head there. So I think of those rides at the fair that have the chains. I think it's called the yo-yo. If you sit in those and they spin you around and around and around, if those chains broke, you go flying off into the fairground. Now gravity would be an unbalanced force, and you'd fall like a projectile, but you go flying off in the direction of where you were at that moment, what direction your velocity was at that very moment. That's circular motion. So the question then is, what is keeping this object in uniform circular motion? What is keeping the object changing direction? Let me do one more right here. If the object were right here, its velocity is off in that direction right there. So I kind of gave it away earlier. I probably shouldn't have said that, but I gave it away earlier. In this case, it's the string that's keeping it moving in a circular path. Well, what direction is the force acting on that object to keep it in a circular path? If this is the free body, just like that, what force is acting on this? Well, it's the tension in the string, and it actually happens to be pulling towards the center. My hand is pulling on that string, causing it to pull inward on this object to keep it moving around in a circle. Once again, if the string was gone, if I cut it right there, it'd go flying off in that direction there. So there's actually a force of tension. Purple, I like purple. There's actually a force of tension pulling in towards the center in each of these examples. Now keep in mind, this was a velocity vector, the red was, but this is actually a force vector. So if we were actually doing a free body diagram, that red wouldn't be there as a force. That red is showing the velocity of the object. So I'll label that V for velocity. So that force of tension is pulling in towards the center. So it's kind of like this. If something wants to move in a forward direction, but if I pull on it like that, pull down on it, or towards the center, I'm constantly changing its direction. And that force doesn't go away the whole time. Every place that it's at, it's constantly pulling towards the center and keeping it in uniform circular motion. That force actually has a special name. That is called the centripetal force. Not centrifugal. Centrifugal is kind of like a make-believe force that pushes outward. It's not really a physics term for a force, but that's called the centripetal force. That comes from two Latin words. One, center or centri, that means center, and then Peter means towards the center or center seeking or falling towards the center is actually what it means also. So you have center seeking. So the centripetal force is literally translated from Latin into a center seeking force. So this centripetal force is seeking the center the whole time it's in motion. It's pulling towards the center. Now the question is, well when it gets here, why doesn't it pull towards the center and fall down like that? Well, this moving object has inertia. It wants to keep moving in the forward direction that it's already moving because it's in motion. So, but when it gets to right here, it still wants to go forward, but at the same time, the force wants to pull inward, so it just keeps moving in that circular path, being pulled inward the whole time, but trying to go forward due to its velocity the whole time. So it's pretty neat. I guess the classic example is taking a bucket of water and swinging it over your head like that. The water does not fall out of the bucket because of this centripetal force. You want to think that the water pushes outward and the bottom of the bucket keeps it in. Well, that's kind of true, but it's that centripetal force. In the case of the bucket, it would be the normal force of the bottom of the bucket that is actually pushing on the water, changing its direction the whole time. Now your arm would be the centripetal force that keeps the bucket in circular motion. This is an overarching term for that force that keeps objects in circular motion. Now there are many things can cause a centripetal force. In this case, tension is what provides the centripetal force. The tension in the string provides the centripetal force to keep that yo-yo or tape in circular motion. What about planets or the moon and our Earth? What keeps those in uniform circular motion? If you said gravity, I hope you did. Gravitational force can keep an object in uniform circular motion. Gravitational force. So the moon orbits around the Earth, and it's constantly changing direction because of that force of attraction between the Earth and the moon. Most notably between the moon and the Earth. Or I should say that backwards. The Earth pulling on the moon, causing it to change direction constantly. So we got tension, gravitational force. What about a car going around a curve? If you took that force away, would a car continue to go around a curve? And I said that force because I didn't give you the answer. What's the answer there? Friction. Friction between the tires and the roadway keep the car moving around a curve or a turn. Take friction away and the car goes, flies off the road and goes in the ditch, and hopefully you don't do that. But if you lose traction or lose friction between the tires and the roadway, you can't continue to turn. So friction is an extremely important force that can provide a centripetal force. So tension, gravity, friction, applied force, a normal force. If you've ever done the Area 51 area, the Gravitron machine at the fair, where you stand there like that, and it raises you up off the floor and you're stuck to the wall. A lot of people say, well, your body is flying outward and it sticks to the wall, but that's not what keeps you in motion. What keeps you in motion is the wall pushing back on your back and your backside. It's pushing towards the center the whole time. Take that wall away and you go flying off into the fair, like I said with the yo-yo ride. So we could put normal force in here. The normal force could supply the centripetal force. So centripetal force, once again, I'll say it again, is an overarching term for a force that keeps an object in circular motion, but that centripetal force can be supplied by a number of forces that we've already discussed in class. Once again, gravity can provide the centripetal force. It's the most important force that provides centripetal force for our planets, for our solar system, and for our galaxy, for that matter. It's a pretty important force that keeps things moving in circular motion like that. So if didn't need that computer anyway, by the way. If there is a, dang, I erased that. I shouldn't have erased that. If the centripetal force is towards the center, I'll redraw it like this. So the centripetal force is towards the center, and the velocity was like this, going off in this direction. So if this is the direction of the motion, like this, can you see how the centripetal force and the velocity compare to each other in my simple picture here? Hopefully you can. They're at right angles to each other. So the centripetal force and the velocity are perpendicular to each other. So let me write that down. So the centripetal force, I'm gonna call it F sub C, is perpendicular to the force. The centripetal force is perpendicular to the velocity. So the object wants to go in that direction. There's a force pulling on that direction, so it changes the velocity. By the time it gets over here, it's already made it curve and it's right there. So the centripetal force is center seeking, and what I was going to ask is this: if and this goes back to Newton's second law. If there's a net force, by the way, this is an unbalanced force acting on that object. It is accelerating. If there's an unbalanced force, then there's an acceleration. And hopefully you remember this statement that in what direction will an object accelerate? Well, that's in the same direction as the net force. So if this is the centripetal force, then there should also be an acceleration towards the center. So the force and the acceleration are in the same direction, and oddly enough, that's called the centripetal acceleration. So not only do you have a centripetal force acting towards the center, you have the centripetal acceleration in the same direction as the net force, in the same direction as the centripetal force. So you have two terms, both centripetal, both center-seeking. You have a centripetal force that pulls things towards the center that causes the centripetal acceleration of the object. The net force causes the acceleration. Well, that's not any different than Newton's second law. Force is equal to mass times acceleration. So this mass, whatever this mass is, that has a velocity, is pulled towards the center with an unbalanced force, causing an acceleration towards the center, which in turn changes the direction of this constantly. Doesn't speed it up or slow it down necessarily, but it changes its direction constantly. So what I wanted to write when I erased that is this. There is a formula for centripetal acceleration. The formula for centripetal acceleration is v squared over r. That means the velocity of this object squared divided by the radius at which it rotates. So whatever that distance is from the center, that's the radius of this entire path. So that's the formula for the centripetal acceleration. There may be a problem at the very end of the first handout over circular motion that you have to do. Not a lot. I think one of the multiple choice questions asks you what is the formula for centripetal acceleration. Well, there it is. And if we know Newton's second law, force is equal to mass times acceleration, well, we can rewrite that and say centripetal force is equal to the mass of the object times its centripetal acceleration, which is v squared over r. Or we could rewrite that as centripetal force is mv squared over r. So that's just rewriting Newton's second law in terms of that. So we know now that centripetal force, all you got to do is take the mass and multiply it by its acceleration, v squared over r. So you end up with mv squared over r for the centripetal force. So that's pretty simple. We're not going to go into some more complex calculations of centripetal motion or circular motion. This is the point in physics where you would start measuring displacement in radians now. That an object, if it moves from here to here, it moves through some radian. That's called the angular displacement. And the velocity that it moves through that is called the angular velocity. Not this velocity, but the angular velocity. So I usually save that for AP Physics. So if you want to take AP Physics next year, you'll get into that. But this is the formula for centripetal acceleration and centripetal force. So I think that kind of catches you up on at least circular motion, how it happens, what causes it, and what's the result of circular motion. Once again, the main idea, the centripetal force causes the object to change direction constantly in a circular path, a uniform circular path, and the result is centripetal acceleration. So that's circular motion. So there's a handout that you had to do on circular motion, and I'll talk about those in just a second. The last thing, and this one's pretty quick, pretty complex, but pretty quick, I'm going to make it easy, is Newton's universal law of gravitation. Newton's universal law of gravitation. And it says this, that there's Newton's universal law of gravitation. that the gravitational force acting on any two objects, it doesn't just have to be really large objects like the moon and the earth, or the earth and the sun, any two objects is equal to this big G times the mass of one object times the mass of the second object over the radius squared. So we'll use the earth and the moon for example again. So the moon's orbiting around the earth like this. The earth is pulling on the moon. We'll call the moon M1. The moon is pulling on the earth. We'll call that M2. And the radius would be the distance between the earth and the moon. But the way it's derived, it's r squared. It's not just the radius, it's r squared. Big G is something that Isaac Newton figured out. It's called the universal gravitational constant. It is a number that basically makes this formula work. It's a constant for any two objects in the universe. You can predict where a planet may be in our universe somewhere based on the motion or the change in motion of objects around it. Basically the gist is this. Let's do some simple math. That if the numerator gets bigger and bigger, well, how's the numerator going to get bigger and bigger? These masses are bigger. So let's say you had the mass of the moon and the earth again. Well, those are pretty big masses. What if you had the mass of the sun in the center and the earth? Well, that just increased the mass drastically. Well, if the numerator goes up, if that number gets bigger, that's not real hard math, then the gravitational force gets bigger. So that's directly proportional. So we'll say as mass goes up, gravitational force goes up. So a direct proportion, not real hard. More mass, more gravitational force between the two objects. However, the distance between the objects, the radius between the objects, if this number gets bigger, if the denominator gets bigger, then this one's going to go down. Not only bigger, but exponentially bigger. If I were to double the size or the radius of the moon out here, instead of being r, if it was 2r out here, well, that would not just double this number right here, it would actually quadruple it, because 2r squared would be 4. 2 squared is 4. It would quadruple this number, which in turn would make the gravitational force go down by a power of 4, not just 2, not just half it. It would go down by 4. So let's say that if the radius goes up, then the gravitational force goes down, not just in a one-to-one, but exponentially. If I were to put the moon 3 times out there, 3 squared is 9. The gravitational force would go down by a power of 9. If I put it 4 times out there, 4 squared is 16. The gravitational force would go down by a power of 16. So it exponentially increases the denominator, which exponentially decreases the gravitational force. So that's why a planet that's or let's say a star that's way out in our universe, it has really not much effect on Earth because it's so far away. However, our sun, which is in relation, based on your frame of reference, to the Earth, is pretty close to the Earth. It has a great effect on the motion of the Earth and the circular motion of the Earth around it. So if you move the sun further away from Earth, it would decrease the gravitational force acting on Earth, and it would probably change our centripetal acceleration around the sun. But anyway, so that's Newton's universal law of gravitation. Once again, there's a lot going on here, but I decided just to give you the gist of it. There is a handout on today's lesson about gravitation as well. So I mentioned the 2 handouts. There's a handout on circular motion. It's mostly multiple choice. There is 2 little free response questions at the end, and there is one on gravitation. Once again, multiple choice, and 2 at the end. They're much like the review questions or the review things I've given you for previous tests. the things I gave you in class to help you review for your test. Same thing. You can use your book on those. If you can't find the answer from my presentation, you can use the book for the answers. But here's what I'm going to need you to do. I'm going to need you to do those. I'm going to need you to send me a picture, or if you have the ability to scan, you can scan them and email them. So I need a picture emailed to me, and I need or a scan of those emailed to me, because I'm going to start grading those over the weekend and next week, and that's going to be your first major grade after spring break. Many of you have asked, what about the work before spring break? You can take all of that work that you've done. If you take it up to the school in the lobby up there, there should be somebody there in the office. You can say, hey, this is Mr. Hall's physics work. I'll probably go up there maybe this afternoon and put a folder up there, and they can stick it in a folder. Make sure you kind of keep it all together. You can put a paper clip, or I don't know how you can do it, what you got at home to be able to do that, but make sure it's kind of all together, the work that you did before spring break. And I'll get you a grade on that as well. So please go to my website under announcements, and it's the second tab on the left-hand side of the screen. There is an announcement for honors physics, and it kind of spells all this out, what the plan is for grading for the next, this is the first week, and there should be 4 more weeks after this. But you do have 2 assignments to do today. We have 2 hours to spend today on work, and it shouldn't take you more than 30-45 minutes to do those 2 handouts if you focus and get down with the book and do those. I did have a question about Monday and Wednesday. Basically what I'm doing is giving you a reading assignment on Monday and Wednesday from the book that is a preview of what we cover on Friday. So it's not actually a written assignment to do. It'll take you maybe 15 minutes to read that in the book on Monday and Wednesday, and it's a preview of the lesson that I do every Friday. So remember, 2 handouts today. Make sure you get those to me. I'll give you till Sunday maybe to get it done, or Monday. But make sure you get those done, email to me, and you'll start seeing some grades pop up in Infinite Campus after you send those to me. So y'all have a great Friday, have a great weekend, stay safe out there, stay inside, wash your hands, and do everything that everybody is expecting of you. And hopefully I get to see you at some point. I doubt before the school's out, but maybe I'll see you next year in the hall. Stop by, say hey. Appreciate it, and y'all take care.